Talk about for the last little part of the first kind of heat balance PowerPoint set here is talking a little bit about heat storage. So really with heat storage, it kind of goes back to that formula. We know we had the heat production variables on one side, the heat removing variables on the other, and then there was the variable S, which was really just talking about heat storage. This is if there's more production than loss, this is what balances the equation. Uh, Again, if we get this to be a negative value, it means overall that core temperature is going to be decreasing. Enough decrease, we get to hypothermia. The opposite is also true if we're not having enough heat loss and we're having too much production, or some of those factors that can usually lead to heat loss are causing heat gains. At some point, we're going to have a buildup of heat to balance this equation again, and that is that positive heat storage, which is going to lead to hyperthermia. Again, there's a number of different ways to measure this. Probably the best when we're talking about exercise and experimental here is esophageal. It's probably the quickest. Rectal is accurate, but generally has a time lag. At least for during activity, that tympanic is not particularly accurate. If you're saying stationary and not doing much, it can be a little bit more accurate. Again, oral temperature is very difficult to measure during exercise, and because you're breathing a lot of air in, it's probably not going to be particularly accurate. So when we have positive heat storage, we start getting above our set point. What's going to happen here is the hypothalamus is going to start activating cooling mechanisms. So we are going to sweat, get that heat loss through evaporation. To get rid of 1 gram of sweat, it takes a decent amount of energy. We can sweat through a number of different types of sweat glands, but it's mainly those eccrine or merocrine sweat glands that are on the forehead, the back, the palms. These are going to help to cool us off. The other thing we're going to do is move that blood closer to the evaporating liquids, which is going to help with that dissipating the heat. Also, any convection or radiation, it's going to increase those effects a little bit if, again, environmental conditions are set up for that to happen. Obviously, if it's warmer than the body, it's going to be hard to radiate heat off the body. Again, the other way it can happen as well, when we start getting below that set point, that negative heat storage, what we're going to try to do then is come up with ways to generate more metabolic heat. The biggest one of this is through shivering. Again, with shivering, you can increase that metabolic heat production up to about 5 times normal. Again, generally determined by kind of the skin temperature and how big a difference it has between that core temp. The other thing we're going to do is to reduce radiative heat losses and reduce convective heat losses. We are going to vasoconstrict and try to keep more of that heat inside the body. We do have piloerection. It really doesn't help us too much. We generally don't have enough hair to trap that air against the skin. Again, but we still have that effect. What gets interesting is when you start talking about certain jobs, for example, like the firefighter. If we go back to the equation, the heat balance equation, they're going to be having a lot of heat production. They are moving a lot. They are carrying a lot more weight. That's going to generate more heat production. They are not going to have much in the way of conduction or convection taking place because they're covered in protective clothing. Because we are also covered in this protective clothing that's impermeable to water, there's going to be no evaporative cooling taking place. And because of the environment in the end where they're fighting a fire, the environment is actually radiating heat at them and is going to be a heat gain, not a heat loss. So you can see with firefighters, the propensity to have a lot of heat gain and get hyperthermic is a big issue. So to kind of give you an example where this kind of graph works together, we're going to end up with that positive S, which is going to lead to an increase in core temp. The other thing we have to keep in mind is a lot of these work under certain conditions, but depending on the environment, how well we can evaporatively cool, how much sun there is, how much we can radiate away. Some of this is going to be very dependent upon the environment. So things like air temperature, humidity, how much air movement there is, what is that kind of radiant temperature, how much sunlight is hitting you. These are all things that are going to play a role in some of these heat loss mechanisms. So air temperature, and they can actually do these type of thermometers. It's actually kind of like three thermometers in one that are used to really determine, like when we start talking about like heat indexes, that's what they use, not just a thermometer. But air temperature, they use just a thermometer. So this would be a glass thermometer, mercury alcohol thermometers that are just measuring that kind of kinetic energy in the air. Radiant temperature, this is again because of that electromagnetic spectrum that's being irradiated from the sun. If there's more sunlight hitting you, you are going to absorb more radiation and it's going to heat you more. So the way that we can use a thermometer to do this is you have a thermometer in a black globe that is going to absorb that radiation, and therefore is going to give you an idea of how much that radiative heat is playing a role in what your body temperature is actually feeling. So, and again, if you don't remember the different temperature scales, there's Celsius and Fahrenheit. Here's kind of the comparison of how these work. 98.6 is about 37 degrees Celsius, but you can see here is the conversion factors. You can also measure stuff in Kelvin, which is just Celsius plus 273, getting us down to absolute zero. Again, some of these different measurement scales. The other thing that you have to pay attention to is how much of convective heat loss or gain that might be going on here. So they can have these anemometers that are actually talking about how much air is being moved past this particular thermometer. So you can measure air velocity. And then finally, you can also measure humidity in the air by having a thermometer that is kind of in the liquid. You have this one kind of giving you an idea of how much really water the air is capable of handling. So what is the vapor pressure in the air relative to some type of liquid? If that vapor pressure in the air is higher, this saturated kind of water vapor that this thermometer is in, it's going to have a harder time evaporating, and that can give us a percentage of humidity. So again, that humidity is going to be kind of a combination of the air and then how much more it can take till no more water can go into the air. The higher the humidity, basically it's saying the more water vapor is in the air and the less that it's going to be able to take on. And you can actually see these with these kind of setups like this. So a lot of times at like running events, for example, like marathons, they a lot of times will be taking a temperature this way where they're getting a true heat index of what the really kind of that feels like temperature is going to be like, which is going to be a better indicator of heat balance and not necessarily just what is that ambient temperature. But I mean, again, ambient temperature, if it's hot with the having high humidity and it's a very sunny day, that is, in terms of heat balance, is going to be much harder for you to maintain heat balance than if it's just a warm day, low humidity, and overcast, for example. So all these things do play a role, not just the ambient temperature. And again, by measuring it this way, we are looking at conduction, convection, evaporation, radiation, all these kind of combinations together give us what is called this wet black globe temp. So you kind of get all these together and it can kind of give you an overall idea of what is that actual kind of environmental conditions, how they're going to affect heat balance. Again, some of this graph as well in terms of heat balance is going to be also how much are we producing. Just being alive is going to produce some heat. The more activity you do, the more heat you're going to generate. Very little of this is going to actual work. So we have, honestly, a really hard time measuring calories. But we have some base metabolic kind of estimations here where that metabolic rate is going to be about 45 in terms of lying down, where you can see if you start going to 5 kilometers an hour, you are generating a lot more heat. If you were running at 10, 15 kilometers an hour, you can see that number is probably going to be even higher. And again, the more active you are, the more heat you're generating, the more we have to bring in some of these heat dissipating mechanisms to try to balance that out. So you can see Homer here on the couch. He's not being particularly active, so probably little heat production, also low insulation. So chances are, if in this case, he wouldn't be having much in the way of heat loss or heat gain, so probably close to zero on that one. So therefore, any heat he is producing is being lost through those other mechanisms pretty easily. And again, because it's an inside environment, the temperature, the radiant temperature, humidity, and all that are not playing a role to really affect Homer's ability to maintain heat balance. So the last thing I really want to talk about on this one is really just kind of getting a look at some of the mechanisms of thermoregulation. Kind of what we've talked about in A&P is you kind of have this set point and a couple different negative feedback loops that can work in either direction. In reality, it's a little bit more complex than that. There's still some controversy as to exactly how we do it, but if we were kind of going with a generalized A&P model, your mechanism here is like you're kind of like a house thermostat, where if you get out of your range, you turn on the heating, you turn on the cooling to either shiver and generate more heat, to sweat and reduce that heat. So that's kind of like your body's air conditioning. The main issue with this is we have graded responses. You can shiver a little bit, you can violently shiver, you can sweat just a small amount, you can sweat a lot. This also is not very good at explaining how we can have that set point move a little bit with fever or steady state exercise activity, that you can have a temperature that is stable and above normal. Definitely there is some support for this. The hypothalamus does respond to hot or cold. There's definitely a lot of sensory nerves throughout the body and within the core and periphery that can measure this. So there is some support for this model, but chances are it's a little bit more complex than that. Reciprocal inhibition is similar to that set point model, but just kind of saying the receptors and sensors and effectors are a little bit more interconnected. And really it's kind of a combination of these things that are protecting against heat loss or heat gain. So for example, if you are your body temp is going up, those heat loss mechanisms, while they are working, you also should be inhibiting some of those heat gain pathways. And what supports this one a little bit is that this works even if you have some hypothalamic control being lost. So if you block hypothalamus activity, you can still coarsely regulate your body temperature. And if it was a set point with a thermostat, that doesn't necessarily work. The last one here is more of kind of not so much regulating the temperature as much as regulating heat storage. And what this is kind of saying is we are trying to make sure we don't gain or lose heat, but we're not measuring temperature as much. We're trying to not have heat gain or heat loss. So heat storage is what's being regulated, not necessarily temperature. And a good example of this one is we actually see it with running in a lot of steady state endurance activities. You're going to see a temperature spike, and that temperature spike is going to stay pretty consistent, but it will spike up because you generate heat faster before those cooling mechanisms kick in. But what usually happens if you get into a steady state, the amount of heat production generally gets matched up with those heat dissipation mechanisms, and you get to a state where you might have gained a little bit of heat, but then it kind of balances out and we're no longer gaining heat. And then post-exercise, those effectors stay active a little bit longer and dissipate that excess heat and get us back down. Again, this one would require us to be able to measure heat flow, so from the core to the shell, to make sure that we are dissipating that heat. But this can be accomplished, and we do have receptors at differing depths. At least with activity, this seems to be probably one of the ones that is a little bit more, I don't want to say correct, but more supported on that one. But again, there is not a kind of a field-wide agreement as to how exactly we regulate this temperature. But these are some possible explanations. And to me, on these things, I would say be able to understand how we're saying each of these would work and have a good understanding what about the strengths and weaknesses of each model would be. So I believe that's about it. So I will see you next time.